This is a question from January 09. It's question 7. Figure 7.1 shows a network of 5 resistors connected between X and Y. And so you can see X and Y, and I'll just scan in a wee bit so you can see it a wee bit more clearly. Right, so you've got a 4 ohm, a 6 and a 12, and a 6 ohm and a 3 ohm. And the first question there is just to calculate the total resistance between X and Y. So I'm going to just maybe turn this on its side a minute, and we'll do this very quickly. This parallel part here is going to be equal to 1 over 6 plus 1 over 3. So that's 1/6 plus 2/6 gives you 3/6. And therefore the parallel part is 6 over 3, or 2 ohms. For this part here, we've got 1 over 4 plus 1 over 6 plus 1 over 12. So that's going to give you in twelfths, 3/12, 2/12, and 1/12, and in total that's 6/12. And therefore the parallel part for this bit is 12 over 6, or 2 ohms as well. So we've got a total of 2 and 2, and therefore when we finish off the total resistance between X and Y, 2 plus 2 is equal to 4. And the total resistance is 4 ohms. It then tells you the current entering the network at X is 0.6 amps. Calculate the current through the 12 ohm resistor. So just to show you where X is here, and therefore the 0.6 amps is going to split up between each part. So I'm going to find the total voltage in this part here, and then I'm going to use that voltage and use the resistance, 12 ohm resistance, to calculate the current in this bit alone. So the total voltage in the top part is equal to I times R. And I know the current flowing through it is 0.6, and the total resistance of the top part is 2, and that gives me 1.2 volts. I'm then going to apply this to just the 12 ohm resistor. So just the 12 ohm resistor, I is equal to V over R. So I know, because the total voltage in the top part is 1.2 volts, that means every branch of the parallel part gets 1.2 volts, and so there's going to be 1.2 volts divided by the resistance, which is 12, and that gives you 0.1 amps, and the answer is 0.1.